everybody. I'm Christopher Crosby. I'm a partner engineer here at Google Cloud. So what that means is that I help our partners in the data and analytics space, such as Hortonworks here, either build, move, or integrate their products onto the Google Cloud platform. And I'm actually really excited to be here, because before I came to Google and was partnered with Hortonworks, I was actually a Hortonworks customer. I was the data science manager at a large cancer institution in New York City. And when we were there, we had this really great enterprise data warehouse. The data in it was just pristine. Everything that was supposed to joined together. Hundreds of ETL processes ran every night. We had workflows that could go through and make sure that data got corrected when errors were found. However, what we found was we would build these models off that data. We'd have these great AUC curves and everything, but then when we went to actually put those into production or put those into an actual workflow, they fell apart on us. And that's because the data that we actually had access to in real time was very different than that pristine data warehouse data. What we had in real time, that data was unstructured. It was tons of duplicates. It was riddled with errors. So what we did is we worked with Hortonworks. We set up a small Hadoop environment. We could start collecting all of those various transactional messages that were flying around the hospital during the day. And so with that, we can start building our models on top of those data structures with the goal of hopefully giving us much more accurate models, because it was based on data that actually represented what was available. So it's been a lot of fun for me to first be on that customer side of Hortonworks, but now to be partnered with them and getting to take a peek a little bit behind the curtain and see how this product is actually developed. So hopefully with today's session, I can give you some of those insights too. So here's an overview of what we're going to talk about today. So first of all, I just kind of set up where we are with the Google and Hortonworks partnership today. I'm then going to lift the hood a little bit on Google Cloud Storage and how that integrates with Hadoop, and a couple differentiators you should know about if you're used to working with other object stores and Google Cloud Storage. Then I'm going to hand off to Sid, one of the principal engineers at Hortonworks, who's going to give you an overview of hybrid environments and enterprise security, as well as give you very prescriptive guidance for how you should be deploying Hortonworks on Google Cloud. And then finally, John, product manager from Hortonworks, has an awesome demo with Cloudbreak on Google Cloud, so you definitely want to stick around for that. So, to get started, where we are with our partnership. Hortonworks and Google Cloud accelerates next-gen big data in the cloud. All right, so obviously that's a line that came to me directly from the marketing folks. But what does this actually mean? What this means is more options for hybrid Hadoop deployments, as well as extending your enterprise applications into the cloud. So the way this is actually done is the GCS, the Google Cloud Storage Connector for Hadoop, is now integrated into the Hortonworks platform, and it's fully supported. Hortonworks Data HDP, as well as Hortonworks Data Flow, HDF, are both fully compatible with the Google Cloud Platform, integrated and supported. So what does this actually mean to you as a customer? What features can you expect? Well, you could definitely expect more agility and ability to run ephemeral HDP workloads. You should also be expecting to maintain those same enterprise applications and extend them into the cloud. So more specifically, things like your metadata management tools. You should be able to take those and extend that into the cloud. You're no longer have to break your data lineage if something goes into the cloud. Same thing with your security and compliance models. Those are going to be consistent now between on-prem and the cloud, so you don't have to necessarily go through and redevelop and re-audit everything for security. Now, we're going to talk about some of the caveats with that later. Sid's going to address that. But in general, you'll be able to take those same paradigms and move those to the cloud. And of course, all of this is going to be 100% open source. Both Google and Hortonworks are very aligned in terms of making sure that we are contributing back to the open source community. And so both the GCS connector as well as Hortonworks are committed to making this 100% open source. So before we get to the new Hortonworks model, just to level set, I do want to talk briefly about something that's existed in the cloud for a while, and this is the Google Cloud Storage. This can be used alongside HDFS, the Hadoop file system, to separate your storage from your compute. You can make this your persistent storage layer. And the advantage to this is now you can start to scope your jobs or scope your clusters to the job. So instead of spending a lot of time building these Spark configurations to send to a multi-purpose cluster that's going to then go compete for resources, what you can do with things like Cloud Data Proc is if you have a machine learning heavy job, you spin up a compute heavy cluster, send your machine learning job to that. If you have interactive analysis job, so things like Hive, or you want to have a lot of a BI layer, that can just be a memory heavy cluster and you send jobs to that. And Dataproc has a lot of features such as workflow templates that will help you build these. And we have customers like our friends at Spotify Labs who actually created a framework called Spidra that sits on top of Dataproc that will also help you dynamically size these jobs. But with this Hortonworks partnership, what we really are able to do now is we can start to mix and match entire Hadoop distributions along with the job sizing as well. And so that architecture, it's really powerful. And if you use it correctly, this is also going to be a big cost savers as well. So the idea here is that now pointing all to the same source of data, your HDP users, those folks that just spent the last 5 years learning Mbari and are happy with it, or your data analysts that really like working in the Hive web interface with TES, and they want to keep all of that, all those enterprise features. They can simply move that to the cloud. However, as you're finding some jobs that maybe don't require a lot of those enterprise features, you can spin that, like nightly ETL jobs is a good example of that. You can start to spin those off into short-lived Dataproc clusters and save some money. Also, because all the compute and storage is decoupled, you can have more experimental clusters. Things like maybe your data engineering, your data science team, they want to start experimenting with Spark 2.3 running on Kubernetes. They can still be pointing at the same data sets that all your enterprise HDP users are using. Now, I think it is worth taking a quick pause because we talk a lot about, hey, just replace or use these cloud storage mechanisms instead of HDFS. But I think it's worth a pause to talk about what's actually happening, because there are some changes that take place, especially in the security layer, as you make these changes, and it's worth understanding, what's happening and why. So this, the GCS connector, what that's doing, it's kind of a misnomer, but it's not actually pulling data into HDFS. It is at the block level and over Google's very high performant network, just directly accessing that data. And so Hadoop has this abstract notion of a file system, of which HDFS is just one implementation. You could also use GCS, S3A, and various other systems. And this was originally designed by the folks who were developing Hadoop. It was pretty fortuitous the way they did this. Is you don't want to, when you're working big data, you want to be able to have block sizes of 64 gig, but you don't want that limited just to one disk on one machine. So you abstract that away. You just deal with the blocks of data. And so that works great for both HDFS as well as GCS. However, what that does mean is a lot of that metadata information at the file system level, that's in that storage subsystem, and that doesn't go into the Hadoop layer. So that's important, again, for some security considerations, meaning you have things like Apache Ranger. It's not always the best idea just to slap that onto GCS storage, because that really relies on HDFS permissions and some POSIX compliance things. But we definitely do want to learn more about how this connector works, because there's a lot of benefits to using this storage connector, even though some of the security paradigms change. So, for instance, as we just talked about, you get that direct data access. This is not just pulling data into HDFS. This is actually pulling blocks of data over Google's high-performance network. However, even with that direct data access, you're still going to get your HDFS compatibility. All your jobs are going to work the same. You just need to change the prefix of some of your files from HDFS to GS, and you should be off and running. But with that compatibility, you're also going to get a lot of cloud interoperability. So it makes it very easy when you just have this separated persistent storage layer to move from Hadoop to Spark to even other Google Cloud services. So it's really a great gateway for getting into some of these more interesting higher level Google services like BigQuery. So I was working with a e-commerce company, and their pattern is they start with all of their log data that's sequential output, and they would just run straight MapReduce on that. Then that data they start to analyze with Spark and turn that into these business data marts. So things like, this is mostly for marketing analytics, so it's things like their campaigns or their per customer views of the data. And then they store that in Google BigQuery, and that becomes pretty much their enterprise data warehouse where their data analysts can use it to understand the business better, put their Tableau dashboards and things like that on top of it. And so this is all possible because of the data accessibility. So when you shut down a Hadoop cluster, you're going to lose access to all that data that's sitting in HDFS. It's really tied to these spinning disks. That's not true with Google Cloud Storage. It's separated, so your applications can still access that data, even when your Hadoop cluster isn't running. And of course, even though it's accessible, it's also highly available. And this is done without much of a performance loss. But the really cool thing about both the accessibility and the availability is there's really no storage management overhead on your part. So anybody that's administrating HDFS today knows kind of the pain points of running checks on that data, upgrading versions, doing rollbacks. That kind of work is done, except with cloud storage, it's done by the Google Site Reliability Engineering team. It's not something that your team's gonna have to carry a pager for, so it really helps with that overhead. You're also gonna get quick startup. So typically with HDFS, you don't get to start running jobs until your name node comes out of safe mode. With Google Cloud Storage, as soon as your workers come online, you can start to access that data and process that data. And a lot of customers that we're working with over time have told us that that's a cost savings because Google Cloud is something that bills at the per second level. So if you're talking about minutes every time a ephemeral cluster comes up for a specific job, over time, that's going to be a significant cost reduction for that quick startup. You're not going to be paying for the inefficiencies of startup times. And then finally, you get integrated into the Google Cloud security ecosystem, and you'll get to take advantage of all the cloud security. But again, I definitely want to point out, this is great that it gets you in there, but you want to be aware of the changes that do occur because they're different storage subsystem, and you're going to have to manage these different storage subsystems, HDFS and Google Cloud Storage, a little bit differently. So a couple quick tips for working with Google Cloud Storage. You definitely want to be taking advantage of our different storage classes of GCS. So other object stores that you might be accustomed to working with, they have separate API calls where if I put something into an archive or cold storage, I have to call a separate API, restore that in 4 hours. All three of these storage classes are the same API calls, same system. Your jobs will work the same between regional storage or nearline storage. It's just a matter of where you put them. So regional storage, that comes in two flavors, multi-regional or regional. And this is where most of your data is going to live. This is what you're going to use for your interactive Hive or Spark analysis. And the rule of thumb here is basically any batch job that will occur more than once a month. Now, nearline storage is the next tier down. And this is really for batch jobs that you're going to use for historical reporting or aggregations. Rule of thumb here is if you're going to touch data about once a month, this is nearline storage. And then finally, cold line storage comes into play for that post-process data. Stuff you probably don't think you're going to use again, but you want to keep it around just in case, or maybe you have compliance reasons to keep it around. Rule of thumb there, if you think you're going to touch it once a year or less, cold line. Now, next tip is don't be afraid to use GCS as a destination. So GCS, Google Cloud Storage, we provide strong global consistency for a lot of those operations that are relevant to Hadoop. Read after write, read after metadata update, read after delete, bucket listing, object listing. So some other object stores you may have worked with, they're eventually consistent. So to get around that with Hadoop, you have to build some kind of kludgy architectures where you might have a NoSQL database that sits in between the object store and Hadoop that's going to keep track of what the files are actually doing, what's available. For the most part, that all goes away with GCS. You can just use it as a destination. Now, there's a couple outlier cases there, such as like a rename still not atomic. But what our customers have told us that for the most part, it works fine for the vast majority of use cases to use GCS as a destination. So if you want to get started with this, you can go try it on pretty much any Apache Hadoop system that you have, all you have to do is drop a single jar file into the class path, and you can pull that jar right off of our GitHub repo. Starting in release 1.9, it's going to work with both Hadoop 2.3 and Hadoop 2 and 3, and then you just have to configure the permissions. So if you're in Google Cloud Storage or Google Cloud itself, definitely take advantage of service accounts for this. That'll give you that transparent token exchange. But if you're coming from on-prem or a different cloud, go ahead and you can set those credentials in the core site file. So with that, I'm going to hand over to Sid, who's going to talk more about hybrid environments, enterprise security.
Thanks, Chris. So I'm Siddharth Seth. I work as an engineer at Hortonworks. I've been associated with a bunch of Hadoop projects, Hive, Blaze, Yarn, LLAP, for about 7 years now. So before getting started, I'd just like to set some context on hybrid environments as well as security, which will be useful later on in the talk. So first up is the Hortonworks Data Plane service. So this service lets you manage your on-prem as well as cloud clusters in a single environment. It gives you a view of all of these clusters. So the Data Plane platform itself lets you run services on top of it. And that's really where you get the value. Some of these services are the Data Steward Studio and Data Lifecycle Manager, which are already available. And what's coming soon is the Data Analytics Studio, Cloudbreak, and it's possible for additional services to be added to the same platform. The Data Plane platform provides an interface to access these clusters, as well as user management and role management for the services. So DSS and DLM are two services which I'll talk about today. DSS lets you manage your data sets, whether they're on-prem or on cloud storage. You can view the data sets, you can view access patterns. It comes with a view which lets you look at audit information to see who has accessed the data essentially the access patterns on the data. It also comes with a few profilers. A very interesting one over there is the sensitive data or PII data profiler, which can scan through your data sets and figure out, essentially it can go and tag sensitive data at a column level or at a data set level, which then integrates later on with Atlas and Ranger, and we'll come to that. DLM serves as DLM is the Data Lifecycle Manager. It provides it's responsible for data and metadata replication. So it lets you replicate data between on-prem as well as cloud environments. It also serves as your disaster recovery solution, because it's replicating both the data, metadata associated with, say, Hive tables, as well as your Ranger audit policies or any security policies which you have in Ranger. All right, so while it's great that we can run Hadoop clusters, if you look at very simple Hadoop clusters, you have storage and you have compute. Very often that's not enough for enterprises. It's great that they can run their jobs, but enterprises require governance and security in place. Towards this, there's several components. There's NOx, which serves as perimeter security. Especially in cloud environments, you don't necessarily want to expose all of your endpoints over the public cloud. NOx secures all of these public endpoints. The Hive Metastore, of course, has metadata about your tables and data in general. And we'll talk a little bit more about Ranger and Atlas. So Ranger gives you, for people who haven't used these products already, Ranger gives you authorization policies for your data. So this can be at, let's say, at a database level, at a table level. In addition to that, what's very important here is it gives you fine-grained access control. So you can potentially go and say that a certain column is sensitive data, flag that, and set up a policy to say that only certain individuals or certain organizations have access to this data. If someone else were to try to access the data ends up getting masked when running a Hive query. Another piece over here is tag-based policies, and we'll come to that when we put all these systems together. Apache Atlas is for governance. So this keeps track of data lineage, as well as data classification. So when you generate a new data set, you'll be able to say what the source data sets were to get to this data. That information is always tracked. Atlas also has, it's integrated with most parts of the Hadoop ecosystem, and it has APIs for integrating with external components. In case you have an external data source and you're bringing data in from there, it has APIs to integrate with that. Now, putting all of these together, let's say DSS, Ranger, and Atlas, you could end up saying the DSS sensitive data profiler runs to tag sensitive data on all of your data sets. That then sets up tags in Atlas, or you could manually set up tags in Atlas. And after that, you set up policies in Ranger saying that any data with this specific tag is only accessible to users who are authorized to use that data. And this provides a very powerful abstraction for the entire security mechanism of securing your data, making sure you have an audit trail. Ranger takes care of the audit for all of your data access. So that was just to set context for the rest of the presentation. So deployment architectures for the cloud is what we'll talk about next. So this is a diagram of your typical on-prem deployment. Now, these are typically long-running clusters. They're shared by multiple users. Resource management is handled by yarn queues. Different organizations can end up sharing the same cluster. They'll have allocations within yarn queues. This cluster is secure, will typically be secure. You'll have authentication in place. It's tied to your LDAP. Kerberos will be in place. Data sits on HDFS. Temporary data is called out separately over here. It sits on the same HDFS. It's called out separately because we're going to iterate on this diagram further down. There's a metastore. There's Ranger, Atlas. Atlas isn't explicitly called out here, but there's Ranger, Atlas in place for your security and governance. Very important here is also that all of these components, this cluster is long running. It needs to be reliable. It's all the masters are highly available. This is a simplification of the same diagram, which we'll iterate upon further down. Again, data and temp data here are the same HDFS. They just called out so that we can iterate on this diagram. So it's as a first step, it's very tempting to kind of say, okay, I have an architecture on-prem. Let me just take the same thing, provision VMs on the cloud, and run the same architecture on the cloud with data sitting on HDFS. Now, while that in theory is simple to reason about, it's not really the best way forward. The main problems here are, one, is data sitting on HDFS, which means if you can't really scale your cluster that well. If you remove, while HDFS data is replicated, if you remove enough nodes, you will end up losing data. Alternately, you can use persistent disks, and then you'll have to deal with reattaching disks when you scale up or scale down the cluster. So it's not necessarily the best mechanism to use when migrating to the cloud. All right, moving on to some cloud deployment models which can be used. So you need to start thinking a little differently when moving from on-prem to cloud. Now, all of these deployment architectures serve different use cases and can be used. The first one here is very simple, a ephemeral cluster. The pieces in the red outline are optional components. So your first step is to say, I'm going to have compute. I have a temporary HDFS only for temporary data on the cluster, and the main storage goes to GCS over here. And in this system, Hadoop security is optional. You can instead rely upon cloud security, which includes IAM, network security rules, to make sure only certain people have access to the system. There's no metadata. There's no metadata when you get started. You can attach a metastore to it if you want. You can attach Ranger policies at a later point, but you end up redefining the same thing over and over again. It's great for ad hoc jobs, though. Moving on is where we introduce shared services. So at this point, what we're doing is we take the metadata and we split the cluster into two different entities. We have the shared services cluster, which at this point becomes a long-running system. It's always on. Other clusters will be launched and will attach to this. Again, in this model, you can rely. Hadoop security is optional. It's very similar to the previous one. The main data sits in GCS. The advantage we get over here is that the metadata is always available. It's easy to discover data. You can attach as many clusters as you want, and all of them will see all of the metadata and will be able to access the data via GCS itself. If you do want authorization, you will again define a new Ranger, and Atlas, and you will connect to that. But you will have to redefine your policies. Now, this is a system which works really well. A use case for this would be development environments. So as an example, in Hortonworks, this is used extensively where we've pre-generated some data sets on GCS. The metadata is sitting in Cloud SQL, and we attach a metastore to it. And whenever we need to try out new code, do some testing, etc., we'll spin up a new cluster, do the testing, do the experiments, tear it down to save cost. So taking this to the next level, and this is where we get into the enterprise security space. We're going to move Ranger also into this shared service cluster as well as Atlas. Again, it's not called out over here, but Ranger and Atlas now move into the shared services cluster. It's long running. Very important distinction here is that Hadoop security becomes an important aspect. There's not a lot of point doing authorization if you're not authenticating the users. So data sits in GCS, connect as many clusters as you want, spin up new clusters, they'll have their policies available, they'll have the metadata available, all the performance optimizations which come with the metadata will be available on this cluster. And yeah. Okay, so just a recap of the shared services. This is essentially what your system will end up looking like. There's going to be one long-running shared services cluster to which you're going to attach. It's plugged in with your LDAP. It's plugged in with Kerberos. You can attach as many ephemeral clusters as you want to launch jobs, or you can have long-running clusters utilizing the same metadata, same policies. Long-running clusters. This is completely up to the way organizations want to structure their Hadoop systems. An example of a long-running cluster would be an LLAP cluster, which is serving dashboards. You don't necessarily want to spin that down because it's serving a dashboard. So you just attach the same cluster, have your policy enforcement, have your metadata, all of that managed via this. Now, this is where you really get the agility of the cloud. Because one, you get capacity on demand. So if on-prem, for instance, you've run out of capacity on your Hadoop deployment, it takes a long time to get new servers in place. A lot of organizations don't even want to get new servers. You would just provision a few more instances on Google Cloud, and you have new capacity. The other big advantage here is you can leave your existing workloads running on. You may have pipelines already in place, some stable workloads which run on a schedule, but you want to try out newer versions of software. You may have Spark 2.3 or a newer version of Hive, newer version of Spark. You can just launch a separate cluster, which will attach, again, to the same shared services cluster, play with it. Once you're happy with it, you will migrate it over to you will migrate your production environment over to this. And of course, similarly, you can set up test instances against the same. Another paradigm is lift and shift with data on GCS. This is a very feasible option. Some things to keep in mind. There's very few HDFS nodes, so in theory, it's easy to scale. The other thing to keep in mind over here is if it's multi-tenant, a single long-running job can prevent scaling of the cluster because there's intermediate data, which cannot be lost. Otherwise, a job will have to end up rerunning stages. Okay, so this talks about the cluster shapes, irrespective of whether it's a shared service cluster, ephemeral cluster, or long-running clusters. There's master nodes. There are nodes which run a temporary HDFS as well as double-S compute. And then there are compute-only nodes. Depending on the kind of performance you want for your workloads, you would run all of these on non-preemptible VMs. And to save cost, you can always run the compute-only nodes on additional preemptible VMs. Hadoop knows how to recover jobs in case nodes go away, and it will take care of all of this for you. So this talks about how the various Google components, Google Cloud components which are used. HTTP, HDF will run on Google Compute Engine. Ingest, you will bring your data into GCS. You'll write your data out to GCS. The shared services cluster, you'll use Cloud SQL for Ranger and the Metastore. And the shared services cluster, again, runs on Google Compute Engine. Logging and monitoring can be integrated into the shared services cluster, and part of the logging and monitoring would go in over here, where we have metrics via Ambari. The other parts, system logs, could go into Google Cloud logging infrastructure. All right, so covering some recommendations which are very specific to Google Cloud. So some things to keep in mind is that disk performance scales with the size of the disk up to a certain point. So size your disks accordingly. Also very important is attached disks. So Google offers local SSDs and a couple of attached disks, either spindles or SSDs. But attached disks count towards network traffic. In fact, they count towards, depending on the type of attached disk, they'll count towards, it'll either be 3x of the actual data being written or 6x, depending on whether it's zonal or regional. So that's something to be aware of, and this will compete with the actual jobs running on the cluster. Shuffle data is, okay, so shuffle data is essentially data which is transferred between tasks during a running job. This is data which, if it's lost, it doesn't matter because, again, Hadoop knows, various Hadoop runtimes know how to regenerate this data. If this data is small enough and for best performance, locally attached SSDs is the way to go because you would not be competing on the network bandwidth. This data is typically for a job transferred in any case between nodes, and there's no real reason to put it onto attached disks. Another important point is to configure independent disks because Hadoop knows how to, if a certain disk goes bad, Hadoop knows to just remove it and continue running with the remaining disks. Temporary HDFS could be a few standard persistent disks. Again, it's temporary, you don't really care too much. All it's got really is scratch directories, intermediate data, things like that. So LLAP provides interactive performance with Hive. It knows how to cache data. It caches data at the column level. It doesn't cache entire files. It can either do this in memory or on disk. So given the performance characteristics of the various disks available, local SSDs is the way to go. The one difference here is combine these SSDs together because it'll work with only a single disk, and combine them together and configure LLAP to use that as the cache. And this can make a pretty big performance difference when running because it's got the data already fetched from cloud storage, it's got the specific columns prefetched, it's got metadata about the information in the cache. GCS, run it in the same region. That's pretty much the most important thing over here. You don't necessarily need to run it. You don't want to be accessing data across regions with GCS. Okay, in terms of the network configuration, the bandwidth on a node is linked to the number of cores. So that's something to keep in mind while sizing your nodes. The workers typically need higher bandwidth, so you would want more CPUs over there. We already covered this, that persistent disk count towards the network limit, so configure things accordingly. Google offers a standard network tier as well as a premium tier. For Hadoop workloads, most of the traffic is within the cluster itself. The standard network tier is more than adequate. And very important is to use private IPs for your within cluster traffic. You do not want this going to public IPs. One, it's an extra hop. Two, it also costs more. In terms of node sizing, this is not very specific recommendations. There's plenty of information available on how to size your nodes. This just talks about the flexibility on Google Cloud. So one thing to keep in mind is that the node size, the cost for CPUs scales linearly. So you can size your nodes accordingly. There's high mem nodes, there's dedicated nodes if required. The other bit here is sustained use and committed use discounts. Now, the committed use discount here is very important because I think, so how it works in Google is you pay upfront for CPU cores rather than instance types. And at a later point, you can decide how to use these cores. You can define different instance types based on these cores. Master nodes, especially in the ephemeral clusters, do not need to be the biggest nodes in the cluster. You're running fewer components. It's absolutely fine to size them smaller. In terms of cluster operations and maintenance, Ephemeral clusters are meant to be short running. You'll typically not run, they wouldn't be highly available. You don't need them to be upgradable. What you're going to do instead is if you need an upgrade, throw away your old cluster, spin up a new one. On the other hand, the shared services cluster is always on. It's all the ephemeral clusters and long-running clusters attached to this. So you want this to be highly available. It has to be upgradable. It has to support running upgrades. So yeah, putting all this together, Cloudbreak 2.7, which is Hortonworks, which is offered by Hortonworks, supports shared services and lets you spin up these environments. HTTP 2.6.5 as well as 3.0 offers GCS connectivity, and yeah, that's how you can play with this. At this point, I'll hand it over to John to talk about Cloudbreak. Thank you.
Thanks, Sid. So I'm going to talk about Cloudbreak today, and this is really about how do we pull everything we've talked about today and pull it together. We've talked about Google Cloud Storage, shared service architecture with ephemeral workloads in the cloud. But how do we actually get to the cloud? How do we get these workloads and start performing big data workloads on Google Cloud Platform? And that's really what Cloudbreak does. It's all about provisioning workloads and pulling in a lot of best practices and prescriptive guidance into the way that you provision these workloads onto Google Cloud Platform. So if we could actually switch over to the demo. All right, great. The best way to really talk about Cloudbreak is to show it live in action. So I'm going to do a live demo today, fingers crossed here, and kind of walk through how you provision HTTP and HDF workloads onto Google Cloud Platform. So the first thing I want to point out here is I have a data lake cluster, a data lake shared services cluster provision, just like Sid talked about. You know, this is an architecture where we're externalizing Hive Metastore data, we're externalizing audit policies and audit logging from the cluster itself into this shared services architecture, and this is something that Cloudbreak supports. So I've pre-created a data lake shared services cluster. You can see here I have a couple external sources set up. I have my Hive Metastore as well as my Ranger database and audit logging externalized from the clusters that I'm going to deploy. So that's what I'm going to do. I'm going to walk through creating a new cluster and show you how easy it is to deploy HTTP on a Google Cloud Platform, as well as attach that to a shared services architecture. So quite simply, I'll click Create Cluster up here. And I can choose the data lake that I want to attach it to get all those shared services as I spin up these workloads on demand. So I'll choose my data lake cluster 3. And my credentials, so these are credentials that I pre-set up in Google Cloud Platform. This is what allows me to instantiate instances on GCP as well as get HTTP deployed on GCP. So let's give this a name. We'll call it Demo 3. Choose my particular region here. I'm going to stick with US East 1. The platform I want to deploy, whether that's HTTP 2.6, whether that's 3.0, or HDF as well. So let's choose a data science workload. Right out of the box, Cloudbreak includes several blueprints. So if you're familiar with Embari blueprints, you'll be familiar with Cloudbreak blueprints. And this essentially lets you define the components, services, and configurations of those components that are going to be deployed in your HTTP cluster. So you can see we have 3 here, one for data science, an EDW workload, and ETL workloads as well, with the common components that would get deployed for those workloads. So let's go ahead and choose data science. We'll click next. I'm actually going to do the advanced UI now that I think about it. We have a basic and advanced UI. The basic UI is really good to get you up and running very quickly. The advanced UI is, if you're going to use the UI, is going to be what most enterprises would do to get all the customizations that they want set up as they provision workloads. So my image settings here, I'm going to use the base image settings that we ship. You can actually create your own custom images. So if you have your own corporate enterprise standards for images for some of the Linux distributions that we support, you can certainly build those images and deploy your corporate standard images, gold standards. I'm going to use the out-of-the-box images we have. hardware and storage. So this is where I can make some adjustments to my host groups. We have a master node, as you can see at the far right. This is going to be my Embari server as well. And we have worker nodes and compute nodes host groups. And I can come in here and adjust any of the sizes for the root volumes, the number of instances that I'm going to deploy. For compute nodes here, let's say we add an instance here and deploy one instance. Next. And we've heard a lot about cloud storage today. That's integrated with Cloudbreak and obviously HTTP. To do some cloud storage here, I'm going to have to put in my service account. And let's put in my base storage location. And then we can attach this to the Hive warehouse using Google Cloud Storage. So cluster extensions, again, we give you very prescriptive guidance in Cloudbreak on how to get these workloads up and running, but we understand, again, just like custom images, there's customizations that you're probably going to need to make. So we have this concept of recipes here. This allows you to run shell scripts, and you can determine at what point during the cluster installation that these scripts are going to run. Like, is it pre-Embari being installed? Is it post-Embari being installed? Is it actually a recipe that runs when you terminate the cluster and remove it, as you would ephemeral workloads when there's no longer a need for it? But again, these recipes allow you to run shell scripts end-to-end. Example of that would be like if you needed to join your host to an Active Directory domain. So you do all the work for that up front, pre-Embari install, and then when you terminate the cluster, there's probably some Active Directory cleanup work that you need to do, and you could have a recipe run at that point. All right, let's go next and talk about external sources. And this is a new capability we launched in Cloudbreak 2.7, is the notion of dynamic blueprints. So very likely, instead of the need to create one-off blueprints for several different configurations that you need, you can have a single blueprint and inject settings into that blueprint. So you can do things like one-time configurations. Common would be if you want to connect these to an LDAP directory and do things like single sign-on. I have an LDAP directory set up here, an Active Directory. You can configure this to connect to external databases. These are probably one-time configuration settings that you want to set up and just be able to easily select those. Next. Now, gateway configuration. Sid talked a little bit about Knox. We have the ability to provision with Cloudbreak and wrap your clusters with an Apache Knox-powered secured gateway. This is great for limiting surface area of ports that are exposed to the public internet and really securing those services that you want to publish for your cluster. So we can do that right here, very prescriptive guidance. We can wrap that. Then we get to the network configuration. We can select existing networks and subnets we want to attach to. We need to make sure in this case, because we're attaching to a data lake services cluster, that whatever selected network and subnet you have defined can communicate with the shared services cluster as well. You can come in here and edit the security groups. You can create a new security group, edit your existing security groups. We intelligently know what services you want to deploy, so we're exposing the correct ports needed for that, like 9443, 9443 for Cloudbreak communication with the cluster, and 8443 and port 22 for SSH as well. And some last security configurations I need to do. Give my Embari admin a password. And put in my SSH key so I can shell into the boxes. Now we do support Kerberos as well. You can enable Kerberos. If you want to do that, there are some prerequisite checks that you need to kind of go through to make sure that that's set up for your environment correctly. If you're just doing some testing and getting up with Cloudbreak really quick to see how easy it is to spin up workloads or try some workloads on your own, you can use a test KDC. We use an MIT KDC, but again, this is only suitable for a test environment, not suitable for production. You should bring your own KDC. And then very simply create cluster. You can see my new cluster being created here. Depending upon how many nodes you're deploying and whatnot, usually takes about 20 minutes here to get through a complete cluster deployment, instantiate all the VM instances, as well as do the Embari install and then add all the nodes to the cluster as well. Once done, your cluster is going to look similar to this one that I've already created and attached to my data lake. You can see here, here's the gateway configuration with all the endpoints for all the services that I publish through Apache Knox. I can see all my external sources that are attached, as well as the cloud storage that I have attached to this particular cluster. One popular feature for our customers is auto-scaling. So once I get on the cloud and I'm working with ephemeral workloads, I can actually resize this workload and add additional compute nodes. I can add additional worker nodes manually. But auto-scaling is a great advanced feature here that we have that allows you to scale up and down based on different events that happen. So for example here, we have alerts, and that's the basics from which you're going to create policies that are going to happen here. And alerts can be time-based. They're based on cron expression, so at particular times during the day, if you want to grow the workload that you have to provision on the cloud, or you need to shrink it, let's say it's a batch job or something that runs at night, and you need to scale up for that. You can certainly do that based on time. You can also do that based on any Embari metrics as well. So based on what you're seeing going on in the cluster, if you need to grow or contract and whatnot, and take advantage of the elasticity in the cloud, you can certainly do that. And then from the auto-scaling policies perspective, again, you can add nodes, you can remove nodes, you can also set the number of nodes to a particular number of nodes that you want, and then you define which host group that this policy applies to. All right, great. So that's it for the demonstration. Just one thing I want to mention real quick, and then we'll kind of go to questions. We got some time for questions. We do have a booth. It's on the 3rd floor. If you're coming from the escalators, it's all the way straight back. It's facing the stairs. So come check us out at the booth. We can do demos for you, talk about any of the products that we have, and answer any questions that you got. So thank you very much for coming.